right, part 3, chapter 10 and 11. So back in translational motion, actually, let's add in back on this table. So we had way we quantified inertia. We've added in here as mass and then moment of inertia. Before we had translational kinetic energy, which one was 1/2 mv squared. So this is kinetic energy. Now we're going to have rotational kinetic energy, which is 1/2 I omega squared. Notice that where we had mass, we now have I, and where we had V, we now have omega. And so we're just going to put these things through here. Unit-wise, just remember this is radians, and then so is this. This is radians per second squared. This is kilogram meters squared. And then this is still joules. Energy is energy. It's still got to have units of joules. So that's kind of where we are so far. So back when we talked about translational motion, the things that what created an acceleration was an F net. F net created the acceleration. F net does that. A net force equals the mass times the acceleration that actually occurs. So the acceleration occurs because you have some net force. In angular motion, angular acceleration occurs because you have a net torque. So torque is this tau. This is tau. It's a little Greek letter tau. Torque is the turning, twisting motion that's due to a force. So torque creates angular acceleration on its own. One torque would do it. So torque is when you see something that turns around in a circle. So and this happens far more often than we think. Actually, the whole human body is just one giant torque machine. Pretty much all the motions that your body does are torques. There's some axis, which are your joints, and then the rest of them sort of move around, and they can move, clockwise or they can move counterclockwise. And that's really kind of what your human body is one big torque machine. In any case, it's easier to sort of think about this, and it's a little more straightforward when we talk about like a door. So if we have a door, there's going to be a hinge, and that's really the axis. And where the axis is very important when you talk about torque. You have to know where's the point that everything's going to try to spin around. And so picking out where is the axis is an important thing. Now, if I push on this door way here at the end with some force, there's actually two vectors here. There's the force vector, but there's also this R, which could be called the lever arm or some sort of thing like that. It's how far away. So R is the vector from the axis to the location where the force is being applied. And the torque is a vector, and it's the vector cross product of this radius vector and the force. So way back in chapter 3, we talked about vector cross products. We have two vectors, and we do a cross product of them. We multiply them, and we get a vector out of it. And so our actual vector here is R cross F, which is not the same as F cross R. It's R cross F. Back in chapter 3, we said that the magnitude of this vector should be the amount of R times the amount of F times the sine of the angle between R and F. The direction of tau would come from the right-hand rule way back in chapter 3. So in this situation, I'm going to take the amount of R, and the angle between my R and my F here is actually 90 degrees, right? It's probably better to draw my F up like this, and then you can see the angle from my R to my F is 90 degrees here. And that actually gives me, sine of 90 gives me 1, and so I get the maximum torque out of this. Another situation would be, say, if I didn't push at the end, say I pushed instead, so we'll go back and redraw these. My door, here's my door. Say I don't push at the end. Say I push at this location and I push at some weird angle. Like I push like this. Right, there's my F. Well, now my angle between my R and my F, so it would be better to draw the F down there, or at least extend it through. Oh, goodness. I can't get it back. All right. So if I extend that F through, I can see that my angle is actually, so the R is like that, so the angle is all the way over, like this. Sine of that would still be a positive number. It's not going to end up giving me a negative torque, which is good because I should just get a magnitude out of this. But I am going to get that it's not very strong, and I'm not going to get nearly as strong a torque out of this. And I think we know that if you push at an angle like this to try to open the door, it's not going to open as well than if you push here. We're also not getting as big an R, right? R is shorter and it's not as long. So the further away from the axis you push, the more torque you get. The more perpendicular you push, the more torque you get. Right? So further away, you get more torque. Mathematically, that's because R is larger. And then perpendicular, a perpendicular force, perpendicular to R, you get more torque. And that's because sine of theta is larger. Now, that's an individual torque. The actual net torque, let me move this down because it got a little lost in the fine print there. The net torque, much like net force, is when you add up all your torques. So maybe you have multiple forces acting on an object, and so you'd have multiple torques. So if, say, my door, one more time with this door, and here's my axis, I could have, say, one force here, and I could have another force there. So then I'd have an R for this force, and I'd have an R for the first force, and I'd have two different torques. Notice that in this situation, force 1 on its own, here, force 1 is trying to create, it's trying to create clockwise motion. So torque 1 would be a negative torque, where F2 is trying to produce counterclockwise motion. And so torque 2 is actually a positive torque. So much as we talked about before, remember that that counterclockwise torques are positive and clockwise torques are negative. We'll do an example here. So this is number 45. It says that the body in this picture is pivoting at this point. So this is my axis. At point O. And the two forces are acting on it, F1 and F2. I'm looking at these. They tell me how far away they're acting, and then they tell me the actual amounts of the forces and some angles there. And it wants to know what's the net torque around the pivot. So first, I'm going to write down, I'm going to say, well, the torque for force 1, the amount of the torque. So the amount of the torque from force 1, this should be R1, F1, and then the sine of the angle, say, between these things. So the actual angle, if this theta 1 is 75 degrees, then the angle from R, between R and F, is actually going to be 105 degrees, right? So phi 1 is 105 degrees. That's the angle from R to F. And so the amount of this torque is 1.3 meters times 4.2 newtons times the sine of 105. And I get the torque has a magnitude of 5.274. Unit-wise, we end up with a unit of a Newton meter. Now, technically, that is the same, it's equivalent to a joule, but in torques, it is not. We do not write joules. The units are Newton meters. It even says it right here. So SI unit for torque is a Newton meter. Now, this force on its own, if there wasn't an F2 over here, this force on its own is pulling this way, and so this would tend to make this object move like this, which is counterclockwise. So this is a counterclockwise torque. Right? On its own, this force is pulling this way, and if it just got to keep pulling along this, and we're moving around this axis point, then this is going to want to move this thing around in a circle, and the circular motion is going to be counterclockwise, opposite the way that a clock would move. I'm going to do the same thing for torque 2. I'm going to say R2, F2, sine of phi 2. Again, they've told me that theta 2 is 60 degrees. That means that this phi 2 is 120 degrees. Yes. So if I plug in R2, which is 2.15, times F2, oh no, yeah, okay, which is 4.9, times the sine of 120, and I get that this torque has a magnitude of 9.124 Newton meters, and it's on its own. This thing would try to make it move clockwise. So when I go and do the net torque, I'm going to say, well, this T1 is a counterclockwise torque, a positive torque, and T2 is a negative torque, and so that has to equal my net torque, which is all that it's actually asking me to find. So I'm going to take T1 magnitude 5.274 and subtract 9.124, and I get a negative torque a net torque of negative 3.85 Newton meters. So this thing is going to want to move clockwise. It has a clockwise net torque. Yeah. Trying to think what else I want to do on these ones. We're going to revisit torque when we get to chapter 12, and we'll do lots more in there with torque. I think you guys may also do number 53, but I may hold off and do that in lecture in Zoom. I do want to add these to our collection here. So previously with translational motion, we had a net force, which was m times a, and this was what creates acceleration, a net force. Now the thing that creates angular acceleration is net torque. And again, it has, instead of the m, it has the I, the moment of inertia. Instead of the a, it has alpha. Instead of acceleration, it has angular acceleration. Units for torque are a Newton meter. Let me see if we can look really briefly at this. So one more thing, for translational motion, we had the work kinetic energy theorem, which said that the net work done by all of our forces was equal to the change in the kinetic energy. This is still true. So forces and torques can do work. Forces are involved with torques, and so we can end up still having work being done, and we can have a change in kinetic energy that's not just a change in translational kinetic energy, but also a change in rotational kinetic energy. So we can have a rotational kinetic energy initially, say 1/2 I omega squared, omega naught squared, and then we can have a final. And the work, translational motion, when we had work done by a force, technically it was the integral of force with the displacement. With the force was constant, this just became F dotted with D. Technically now, though, the torque does work, where it's the torque dotted with the angular displacement. And again, if the torque is constant, we end up with torque times just the change in the angular position, or the angular displacement. Again, very, very similar to what we had over here. So work done by a force was force times the displacement. Now the work done by a torque is torque times angular displacement. So let me run that in over here really quickly on my stuff. The work done by a force was this. Now the work done by a torque is, so we have force, and what stands in for force is torque, and displacement, what stands in for displacement is angular displacement. And so this is work done by a force or a torque. And then power was, instantaneous power was the derivative of work with respect to time, which turns into force and velocity being dotted together. When we talk about torque, it's still the derivative of work with respect to time, but now we've got, again, we're substituting in, we've got torque dotted with angular velocity. I'm not going to add those to the table, but again, we're seeing that every place that we have force, we're putting in torque. Any place we have velocity, we're putting in omega. Any place you have alpha, A, you're putting in alpha. It's just a straight out, everything in those tables will just turn into a new equation, and you substitute the new angular parameter. Let me do this one really quickly, number 61. So number 61 says we have a 32 kilogram wheel. And which is essentially like a thin hoop, right? It's a wheel. It's like a really thin little hoop with a radius of 1.2 meters that's rotating at 280 revolutions per minute. And it must be brought to a stop in 15 seconds. All right, so let's write down some of these things. I've got that the mass is 32 kilograms, and then the radius of this wheel is 1.02 meters. And so I need the moment of inertia to do this. So looking back at this, it's actually got a little hoop. So this is the hoop, and it's this is the hoop because we're going to spin it around this central axis. So again, this is a hoop where we're spinning it around through the axis that goes right through the middle. This is one where it's kind of cutting through the diameter of the hoop. So we just want to use the moment of inertia is mr squared. So the moment of inertia here is going to be our 32 kilograms times the 1.2 meters squared. That comes out to be 46.1 kilogram meter squared. And then it tells me it's rotating at 280 revolutions per minute, and it must be brought to a stop in 15 seconds. So this 280 revolutions per minute, that's actually omega naught, but it's in very bad units. So it's in revolutions and per minute, and I really need this to be in radians per second. So I need to turn revolutions into radians and minutes into seconds. Well, minutes into seconds is easy. A revolution is one time around, right? A revolution is one time around. So one revolution has 2 pi radians. One revolution has 2 pi radians. And you can just write that down and remember it if you don't want to remember to think it out every time. So I can turn omega naught into this, and I end up with 29.32 radians per second. And then it must be brought to a stop. So omega f is 0 radians per second in 15 seconds. How much work must be done to stop it? All right, so how much work must be done to make this happen? So what's W net? W net, right? This is the net. This is delta K. So it's K final minus K initial. Well, K final is 1/2 I omega final squared. And and K initial is 1/2 I omega naught squared. And omega final is 0. So this whole term is 0. And so we end up with a negative 1/2 times our I. So 0.5 times 46.1 times 29.32 squared. This is a negative 1.98 times 10 to the 4 joules. Yeah. So that's the amount of work that has to be done. What's the required average power? Well, the average power is just the work done divided by how much time it took. So the average power is this work, 1.98 times 10 to the 4th joules divided by 15 seconds. Is 1.32 times 10 to the 3 joules per second, or watts. So 1,320 joules per second. All right, so I'm going to leave this one here. It's a little bit longer than normal. I've got a couple more videos I need to do.